Hi everyone, today we have yet another question based on rotational dynamics, and in this problem we have a disk of radius r and mass m rotating with an angular speed omega and is being placed onto a horizontal surface of coefficient of kinetic friction mu. We need to find the time after which the disk stops rotating. Now let us move on to the flow of the problem. We'll have a friction and we'll have an anti-torque due to the friction, which will result in a surface angular acceleration alpha, which will bring down the instantaneous angular speed to 0, and that will be the final angular speed, right? And we have to find this time period. Now a major note to this problem is that the frictional force F is not a constant force, not in terms of magnitude but in terms of relative position of the particles present or distributed along the entire plane of the disk. What I mean by this is that let us consider 2 points A and B. The instantaneous velocity is VA and VB for these 2 points. What I mean by the statement I stated was VB has to be greater than VA. This is because V is equal to x times omega and x is the linear distance from the center. X can have values such as 0 and have the value r for any arbitrary point on the periphery of the disk as well. So we have V is equal to x times omega and VB has to be greater than VA because of the linear distance being greater from the center. So it is an anomaly again. Friction is not constant because we are considering the entire plane of the disk, and of course we're going to have to integrate this now. Now here I have considered a ring element because for a ring the distance from the center of the plane we have is constant, right? So let us say this distance to be x and the thickness of this ring be dx, right? And we need to find the small torque on this ring element. We'll have to find the small torque on this ring element, that will be x times df, where f is the small friction, and for df we'll have mu times normal. Now normal is just mu times the weight, so for weight we'll have g and the mass. Now the mass of this element is something we are aware of. For that we'll have to find the value for sigma. Sigma is the mass density, right? So we have sigma as the entire mass of the ring divided by the area. So we have the mass density as sigma, which is m by pi r square, and for the value of the mass of the small ring we'll have this sigma times the area, and the area for this ring, let us open this ring and let us cut this ring from this end, let us say, and let us open this ring. So we'll have a rectangle of length 2 pi x and width dx. So the area comes out to be 2 pi x times dx for the rectangle. We just opened up this element and nothing else, so the area is now 2 pi x times dx. So we now have the mass of the element we had. So we have the small friction. The value of the small friction is mu g sigma 2 pi x times dx. So from this value we can infer the value of the small torque, which will be mu times g sigma 2 pi x dx times x, right? So it's like mu g sigma 2 pi x square dx. That will be the value for the small torque. For the entire torque to be evaluated, we'll have to integrate this, and the integration will give us the value of the torque. We'll have the value of the anti-torque to the previously rotating disk, and that value due to the friction will have mu g sigma 2 pi x cube by 3. And putting the limits will be from 0 to capital R, because we'll be considering the points on the periphery as well. So now the value for the torque yields out to be mu g sigma 2 pi r cube by 3. So we have the value of torque. Now again we are aware of this relation. The torque and the alpha's equivalence. Tau is equal to I alpha, and we can evaluate the value for alpha as tau by I. So this value of alpha comes out to be mu g sigma 2 pi r cube by 3 times m r square by 2. Solving this, we get 4 mu g by 3r. Now from the equations of motion, we had v is equals to u plus at, and the rotatory analog again will be v omega final is equals to omega initial plus alpha times t. Now the final angular velocity is 0 because the disk will ultimately stop rotating. So the time comes out to be 3r omega by 4 mu g, and that is the answer to the problem we had. That is it again, and thank you for your time.